Hello and welcome back again to our summary of A Brief History of Time. That's right, we are still not finished summarizing this book. We have reached chapter 7. We passed the mid-mark. If you missed the previous episodes, you can go back and watch them. I created a playlist that has every single one of those from chapter 1 through chapter 7, which is the one you're watching right now. If you are also reading the book while you're watching this summary, with my commentary of course, then this will also give it a different taste and it's going to make this a very nice experience for you, which is one of my goals, creating this summary of A Brief History of Time. I know a lot of you have been waiting for a long time for chapter 7, but here it is, back again, which is called Black Holes Ain't So Black. I'm not gonna waste a lot of time, and we're just going to get right into the summary and my commentary, but there are two things that you need to understand specifically about this chapter. Chapter 7 is very different from any other chapter that we discussed before. Number one, this chapter is very personal to the author, who is Stephen Hawking. If you read the book, you're gonna notice that this chapter specifically has more rambling than the other chapters that it preceded it, right? And it also even has expressions of people who he did not like, right? It's almost like he is trying to prove a point by saying the things he's saying in this chapter, which is very interesting and very human, and we are going to get through that. Now that makes it a little bit difficult to summarize, but that's okay. The second thing that you need to understand is this book was written a long time ago. So we need to go into this realizing the ethos and the climate of the time and the state of physics, what we knew, what we didn't know at the time this book was being written, right? For example, right now we have so much information about black holes, but this book was written in a time where there was not a lot of information. The things we know now had to go through a lot of development and things that changed, things that were disproved, a lot of theories and so much work that has gone in these couple of centuries. So some of the information in this book are from that time, but I find that very interesting also, so just keep that in mind. Stephen Hawking, throughout his entire career, was very interested in black hole. Black holes occupied a lot of his work, right? And he just studied that and he created a lot of theories about it. Like I said, he was trying to find out answers about characteristics of a black hole and how do we define it, right? And some of those questions were, where does a black hole start and where does it begin? Which is a very interesting question. This is not a philosophical question. Just think about this for a second. If a black hole is a region in space-time that has so much gravitational pull that it just sucks everything right into it, why don't black holes suck the entire universe into them and we just end up with a black hole? Like a giant black hole, and the universe would just cease to exist because it went inside of these black holes collapsing into a giant one, right? So the question is technically, where does the black hole start and where does it end? Is there an end where nothing affects what's inside a black hole if you were behind that end? And the answer to that is, of course, yes. We now know that this is known as the event horizon, but this is the question that Stephen Hawking was tackling. He was trying to study the black holes after the birth of his daughter, and he used to go to bed and think about these questions. Wake up the next day and he'd write all of these things down. Now, the answer that he came up with, or the definition of a black hole, is a set of events where you cannot escape a long distance from, if you were inside that region, right? So it's basically a region where a set of events would happen, and if you're anywhere near it, then you cannot escape, right? Of course, this is more or less the same definition of a black hole that we have now, this extreme curvature of space-time that even light cannot escape from. And if light can't escape, which is the fastest thing in the universe, nothing else can, right? So this is the definition that he came up with, and he shared this definition with Roger Penrose. He was sharing all of his information that he found with Roger Penrose. Now, Hawking quickly realized that if this was the definition, that means that the edge of the black hole, there should be light that's trying to escape from that black hole, but it cannot escape it. And that light would then form the edge or the boundary of the black hole like this, and this would be the shape of a black hole, right? So it would be kind of like surrounded with light that's trying to escape from it, right? Now, Stephen Hawking likened that to a shadow. So if you were to cast a shadow, you would see kind of like an aura. Do you see how, like, if I put my hand and then there's like a light on top of it, then there is a shadow that looks like my palm, and the shadow would trace my fingers like this, right? So he thought about it kind of like that. He said that a black hole, with the light around the black hole, would basically be around it this way. Now, another characteristic of a black hole that Stephen Hawking thought about is that a black hole would not shrink in size. It would stay the same, or it would get bigger. Now, you might ask, why is that? Well, it's because a black hole would suck everything, right? It sucks matter into it. So maybe it would suck matter into it, and then it would expand, right? Or two black holes would collapse onto each other, and then that creates a bigger black hole. Right? So the characteristic is that a black hole can get bigger, the area around it can get bigger, but it does not get smaller. It has to at least stay the same. Now, there is a way for a black hole to get smaller, but we're going to discuss that later. Like I said at the beginning, this is basically a thought process where you have to progress to what we now know about a black hole, right? So this is what Hawking thought about a characteristic of a black hole. So just keep that in mind. It can increase in size or stay the same, but it does not shrink in size because of that. Hawking has a graph that I'm going to show you right here. You can see this graph is an actual graph from the book. On the left-hand side, you can see a black hole that sucks matter, and then it would expand in size. It gets bigger right here, as you can see. And on the other side is basically two black holes jamming against each other, and they just like combine, and now you have a bigger black hole. Now, what's interesting about this characteristic, where the size of a black hole does not decrease, the non-decreasing feature, is similar to another entity in physics known as entropy, right? Now, entropy also can only increase and not decrease. But the question is, what is entropy, right? Now, this is getting into thermodynamics, so I'm just going to explain this very quickly, because entropy can be complicated to explain and talk about, but I'm just gonna basically lay out a very basic version of it, and you'll understand what exactly I'm talking about. Entropy is basically a degree of disorder, right? Disorderliness. How much disorder is in something or in a system, right? And the law of entropy, or also known as the second law of thermodynamics, is that as time goes by, a closed system goes towards disorder and not order. So it would be more disorderly, right? So everything tends to disorder. Now, there is an example in the book that I am going to explain to you right now very quickly, and it's very simple, just so you can understand what is meant by entropy and disorder and the things I'm saying. I'm going to use the trusty board today. So basically, I want you to imagine that we have a box like this. So this is just an enclosed box. On the left-hand side of the box, I have atoms of hydrogen, only hydrogen, okay? So here would be hydrogen, okay? In the middle of the box, there is a barrier, like this. There is a barrier, and on the right-hand side, we have only oxygen. So I'm just gonna change that just to mix it up. So now, I want you to imagine that the oxygen and the hydrogen are moving around in the small box because there is a barrier in the middle. What happens if I remove the barrier suddenly like this? just imagine it gone. I used my finger for this. So if we remove this barrier, then the hydrogen and the oxygen will start to mix together, right? So when they start to mix together, we have a completely random collision and everything is going everywhere, which means we have oxygen going on this side and we also have hydrogen going on the other side like this. So we have everything is going in all of these random direction and random places. In this case, we say that this system is not very orderly. It has more disorder after I remove the barrier, and therefore it has more entropy. Okay? So that is entropy explained, a degree of disorder. Like I said, the reason he says they're similar in the book is because he says black holes cannot decrease in size, and also entropy cannot decrease, right? It also increases. Systems go towards disorder and not order. Now, the second law of thermodynamics is a very powerful one, which is the law of entropy, and you can't simply violate it, right? This is very interesting. Why do I say that? The reason I say that is because there is a small thought experiment inside the book where Hawking says, I have a way that makes entropy go down, which means this is a way to make the second law of thermodynamics get violated. And it's in accordance to physics. And here is what he thought about. He thought, what if you can take a system with a lot of entropy in it, and you take it and you throw it inside a black hole? What happens now is the entropy outside of the black hole has decreased, violating the second law of thermodynamics. Like I said in the beginning, entropy goes up, it doesn't go down. So he says, if we take a system with a lot of entropy and we just vanish that inside of a black hole, doesn't that mean that the entropy outside of black hole went down? Now, of course, somebody would argue, no, the entropy is still there, but it's inside a black hole. And Hawking says, but there is no way to look inside of a black hole to figure out if the entropy has increased or went down, right? So in this case, we effectively violated the second law of thermodynamics. And if you violated the second law of thermodynamics, there's something wrong with your physics, right? You have to think back again about it, because those laws have to go in harmony. Now, a solution to this that stops the second law of thermodynamics being violated came from a physicist called Jacob Bekenstein. Now, Stephen Hawking did not like Jacob Bekenstein. This is not someone that he was fond of, right? And this is expressed in the book, right? Stephen Hawking felt like Bekenstein took his work and he misinterpreted or used it in his own advantage to advance some of his own work, right? And there's more drama that I'm not going to get into here, but like I said, this chapter is personal to Stephen Hawking, and he expresses that he does not like the work that Bekenstein is doing. Nevertheless, Bekenstein had a solution that stops the second law of thermodynamics from being violated, and his solution is basically this. Again, I'm going to use the board for this. So again, Hawking said you can vanish entropy inside of a black hole, making it go down, and entropy is not supposed to go down. But the idea that Bekenstein came up with the solution is, if you have a black hole here, and you have a system with entropy outside, and you take that system and you put it inside a black hole, like this, he says that the entropy inside of the system is compensated for by the area of the event horizon. What does that mean? I'll explain it to you. It means that, you see the area outside of the black hole, where if you cross, then you are inside of the black hole. Remember when we said, where does it end? That end, the border of a black hole, where beyond it you're inside, outside of it you're outside, this area can't expand and get down. If you throw a system with entropy inside it, that entropy is transformed, and depending on how much there's entropy there, the size of the event horizon will grow. So if you drop a little, the area of the black hole gets bigger by little. So now Wittgenstein's solution is basically saying that when you put the entropy inside, it doesn't go down, it's simply compensated for because the black hole gets a little bigger when you put entropy inside it, a system with entropy inside it. Does that make sense? Now, of course, Stephen Hawking did not like this solution because he didn't like Wittgenstein. But if Wittgenstein is right, then Wittgenstein is right, and it doesn't matter who likes him. Now, Hawking naturally doesn't like the solution, and he says it has a very major fatal error, right? And the mistake is basically this. He says even though this can solve the problem of not violating the second law of thermodynamics, it violates another law of physics. What is it? Here it is. He says basically that if something has entropy, then it has temperature. And if it has temperature, then it's going to have radiation, right? And this is actually an everyday experience. If something is hot, it will glow, it will give a radiation. Given that, provided that the heat is too much. So, like I said, this is an everyday experience, like when you take a piece of metal and you heat it up, and when it's too hot, it glows orange or white, right? And the hotter it gets, it's gonna glow. So it produces radiation because of the temperature. In this context, Hawking is responding to Wittgenstein, and he's saying, this is a system with entropy, which means it has temperature. And if it has temperature, then it's going to have radiation. Question: how is it possible for a black hole to give off radiation when it's supposed to suck everything, not give anything away, right? By definition. A black hole, by definition, is a region in space-time that is warped so much that it captures everything into it, even light cannot escape. So how do you turn around and tell me that there's a situation where you put entropy in it, it's going to have temperature, and therefore it's going to have radiation? It gives something off into the universe. How does that happen, right? It shouldn't happen by the nature of a black hole. Stephen Hawking visited Moscow at some point, and he met two physicists called Zeldovich and Starobinsky, who's still alive right now at the time of recording this video. And I just want you to imagine being an astrophysicist who studies stars, and your name is Starobinsky. You can't make it up. How cool is that? But anyway, the two physicists, Zeldovich and Starobinsky, explained to Hawking that a rotating black hole can, in theory, and should be able to give off radiation. But Hawking agreed to this, but he didn't like the way they used the math, right? The mathematical model that they used, he didn't like it. So even though he liked the idea, he didn't agree with the math too much, so he decided to come up with his own basically structure, and he tried to do these calculations for some time. When he got his mathematical results, to his surprise, and of course he was annoyed, he found out that Wittgenstein was actually correct, and even a static black hole should give off radiation. But this is a paradox, because a black hole should suck things and not give off radiation, right? So now, there needs to be a solution to this problem, because the math told Hawking that this is what happens, a black hole will give off radiation, right? So how can this radiation come? Now, the answer to this question, very interestingly, comes if we look into quantum field theory, right? Basically, the empty, when we say empty, space around the black hole is not exactly empty, right? Do you know how physicists say empty doesn't mean really empty? What they mean is this empty space, yes, doesn't have something tangible that we can touch in it, but it actually has fields. What does that mean? Okay, a quantum field, in quantum field theory, the entire reality is made out of fields. And if that field gets excited, you can get a particle that shows up and pops up. And if there's no energy excitation, then there are no particles. Again, this is not clear. How do I make it clear? I'll explain it. So I want you to imagine this space in front of me and in front of you right now, right? The room you're in has a temperature, right? Does the entire room have like the exact same temperature? No. The truth is, every point on its own may have a slightly different temperature. So we say that in this room there is a field of temperature, right? And the field is basically all of these points combined. Now, in quantum field theory, everything is made out of fields. Reality is actually fields, right? And if that specific field, for example, the gravitational field, has high energy in that region, then there is a lot of gravity because the gravitational field is active. Everything is made out of fields, even like this cup of coffee right here. This solid material is basically a manifestation of an excited field of matter, right? So, in our context, it's saying that the radiation, whatever comes from the black hole, doesn't come from the inside of the black hole because it's a black hole, it should only suck everything. It actually comes from the empty space around the black hole. Basically, around the black hole there are fields, and when those fields get excited, what happens is what's known as a quantum fluctuation, right? And a quantum fluctuation is where a particle or things like this pop up and then they disappear again. Do you see the light that you're looking at that's coming through your screen right now? There are photons, and those photons did not exist seconds ago. They were manifested because of the excitation of the fields that are going on, right? What this says is basically that. Now, in that way, if we take this into account, basically we have a black hole that only sucks everything, and at the same time can give off some radiation, right? And it does not violate the laws of physics, right? So this is basically Hawking's solution to the question that the radiation doesn't come from the inside of a black hole because it can't, but it comes from the empty space around it as a quantum fluctuation, right? And there is a mechanism at play here. I'm gonna have to explain it at the board. First, I will show you the picture that he draws here. This is the picture, and it's very difficult to understand just by looking at it. So I'm gonna explain it quickly in the board. And it says basically this is the region of a black hole. The inside line in the middle is the center of a black hole. This is the singularity. And the edge is the edge of the black hole or the event horizon, right? So outside of here we have a field of particles here. Okay? And pairs of particles appear. When pairs of particles appear, they have two energies, one's positive and one's negative. Now, different scenarios can happen. Let's say, for example, two of them pop here. This is the positive one, and this is the negative one. They will pop up, and then they will join together and annihilate, completely disappear back into the field. And this will look in the field something like this. So this is one, and this is one. They combine like this, and they disappear, right? Now, some particles can appear here, and they just get sucked right into the black hole, into the singularity. Like this. Now, in some scenarios, and this is the important one, you see those two particles? One of them goes into the black hole, but one of them escapes because it's positive in energy, right? Like I said, there's one negative and one's positive. A quantum fluctuation occurs here. And one goes in. This is negative energy. And the pair of this particle would just escape from the black hole because it's positive. And of course it has to be positive in energy because it needs positive energy to actually get it away from the black hole. Now, in this case, if someone was standing here looking at this black hole, he would see that it looks like this particle came from the inside of the black hole. It looks like it came from the black hole. And therefore he sees that this black hole is radiating something away, right? This is basically Hawking's solution to the problem that we discussed. Now, what happens when this one, the negative energy, goes back into the black hole? Something has to happen in the black hole, right? So when this goes in, it gains negative energy. And here's what happens. Do you remember this formula? That's E equals mc squared. The energy goes into the black hole and it's negative, right? So now there's less energy because it gained negative energy, the black hole, and the twin of this particle has gone into the space and has escaped the vicinity of the black hole. So what happens here is the energy decreases and goes down, right? And if energy goes down, the speed of light is constant, so something else has to go down, which is the mass, right here. This solution right here, that when quantum fluctuations occur, and one of the pairs escape, and the other one goes into the black hole as negative, and therefore the energy decreases, the mass of the black hole also has to decrease using E equals mc squared. The implications of this is actually very remarkable, because what this is saying is that a black hole, as it absorbs negative energy over time, it radiates its own mass away into the universe. Its own mass gets smaller as time goes by, and it's converted into radiation as it sucks in the negative energy. Who would have thought that mass can be radiated? But the formula is right here. E equals mc squared. And if the energy goes down and the speed of light is constant, the only thing that has to give in is the mass of the black hole. This remarkable notion that a black hole radiates away its own mass is today known as Hawking radiation. This is not mentioned in the book because, like I said, at the time of writing the book, we didn't call it Hawking radiation. It was named after him later. But it's mentioned here in the book, and I find that really fascinating. This is what he's talking about. Today, we call this Hawking radiation. This is basically Hawking's solution to the problem of how can a black hole suck energy, and it looked like it radiates something, but it shouldn't radiate anything because it's a black hole by definition, right? After he solved this, he went into different realms and studies. Hawking was getting interested in singularities and what's going on in the middle of a black hole, and that took him to a different round of questions regarding what's going to happen to the universe at the end of it, and what was the universe like before it began. Basically, the origin and the ending, or the fate of the universe. He found a lot of interesting answers as he studied this, and he came up with a lot of theories that we know today, and they're common knowledge today, but they actually came from Stephen Hawking. Those things are the things we are going to discuss in the following chapters. Those are going to be very interesting, so stay tuned and make sure you subscribe, like, stay on this channel, share these videos. They are a lot of work. There are a lot of tears and sweat from what I do here. And sometimes I feel like if only a few more people could watch all of this work that I'm doing, all of this great summary, even though I say that myself. So if you can do me the favor, if you enjoy this, please share it with everybody else and check out the links in my description. Everything will be in a playlist. This has been Chapter 7, Black Holes Ain't So Black.